Hello viewers, welcome back to my channel. In this session we are going to discuss the process scheduling. In the process scheduling we have the multi-programming. In the multi-programming, the main objective of the multi-programming is to have some process running at all the time so that we can maximize the utilization of the CPU. So therefore we say that the main objective of the multi-programming is to maximize the CPU utilization. And on other hand, the objective of the time sharing is to switch the CPU core among the processors so frequently that user can interact with each program while it is running. Means one process is running in the computer, right? Okay, let me first complete this multi-programming. So multi-programming means more than one program, right, have entered the computer's memory, and now most of the program means if it is in executing or execution, then it is called process. So some process running at all times so as to maximize the CPU utilization. The main purpose of the multi-programming is we don't want our CPU to keep idle. Okay, we don't want the CPU to keep idle, so that we are giving n number of processes to the CPU, right? So n number of processes to the CPU so that it should always busy so that we can achieve maximum throughput and we can maximize the CPU utilization. That is the main purpose or the main objective of the multi-programming. Now let us come to the objective of the time sharing. So time sharing is to switch a CPU core. So now we are talking about the core. Okay. In my previous lecture, I have already shown you the task manager of my laptop. There I have shown you the 4 core of my CPU. I have physically one CPU, but I have 4 core. Okay, let me write here. I have one physical CPU, but I have 4 core. Okay, so CPU core. So what we are doing, time sharing is to switch a CPU core among processors, right? Means there are 4 core, means if I have more than one process in the CPU, assume that I have 6 process, 6P, I have 6 process. So what I can do, all these 6 process I can assign to the CPU. The time sharing switch the CPU core among the process. It will assign all the 4 core to the 4 processors. Okay. Other 2 process are not assigned any core, right? So those 2 processes are waiting. They have not yet been assigned any core, right? So that user can interact. Means now the 4 process means 4 users are there. Assume that 4 users. So frequently that users can interact with each program while it is running. Now 4 processes are running and user can interact with those programs. Okay, once assume that among these 4 any 2 gets complete its execution, the 2 cores get free and the 2 process which are on hold can get those 2 cores. Okay, so to meet these objectives, these multi-programming and time sharing objective, there is a process scheduler who selects an available process. Available process means, as I said, the 2 processes are there. So these 2 processes are available process. These 2 available process are selected by the process scheduler for program execution at a core. Each CPU core can run one process. As I gave the example of the 4 core and 6 process, if I have 4 core means 4 process can run at a time, right? So if any of the process gets complete its execution, that can leave the core, and the available core, the waiting core can get that core. Sorry, waiting process can get that core. Okay. Now, for a system with a single CPU core, assume that we have only one core. The physically it is one CPU, and logically also only one CPU. Okay. So there will never be more than one process running at a time. Means we cannot run more than one program at a time. Only one program or process runs in a single CPU core. That is the meaning of this point. Now coming to the second, if there are more processes than the cores, then as I gave the example, I have 4 cores. Okay. And more processes means 6 processes. Cores are 4. So here we have more processes than the core. Okay. So the excess, whatever the excess processes are there, they have to wait. Right. They have to wait until a core is free. As I said, 4 core will get 4 processes. Any of the process gets complete its execution, it can leave the core. The waiting process can get that core, the freed core. Okay. So it can be rescheduled. So this is the work of the process scheduler, to allocate the free core to the waiting process. Okay. So the number of process currently in memory is known as the degree of multiprogramming. Now here the degree of multiprogramming is 6. As I said that 6 processes entered at a time in the memory. Currently there are 6 processes in the memory, right? So therefore the degree of multiprogramming is 6. Okay, to balance the objective of multiprogramming and time sharing is also requires that taking the general behavior of a process into account. So in general, the most process can be described as either IO bound or CPU bound. Means most of the process, they will spend their time in either in IO bound process, means in IO devices. If any process is spending more time in IO process, then it is called IO bound process. If any process spending most of the time in the CPU, then it is called CPU bound process. This is the simple definition what I can give for the IO bound process and CPU bound process, right? Let me take an example of P1. There is a P2. Okay, let me have only 2 examples. P1, it's most of the time, assume that, let me just take an example of a 10 millisecond, right? 10 millisecond time is the time of the P1. Let us assume. Now among this 10 millisecond, a 7 millisecond it is spending for IO operation, and remaining 3 seconds it is spending for CPU execution. Then this P1 process is called IO bound process. Okay, taking the same time to P2 also, 10 millisecond, but a 7 millisecond, this is just example, 7 or 8 millisecond of P2 process spending its time for CPU. It is being executed in the CPU, and remaining 2 to 3 seconds it performing IO operation. Then it is called, this P2 is called CPU bound process. Okay, let us come to formal definition. IO bound process is one that spend more of its time doing IO than it spends doing computation. Okay, so in contrast, right? So the CPU bond uses most of its time doing the computation rather than IO operation. Okay. So this is the CPU bond and IO bond. Now, this is the scheduling queues. In the scheduling queues, we have ready queue and wait queue. Now, let me tell you what is this ready queue and wait queue. Ready queue is nothing but as processes enters the system, they are put into a ready queue. So in the already previous lecture, we had discussed about the process state. Okay. So in the process state also, if your process is in ready state, it is the meaning of the ready state is the process is waiting to be assigned to a processor. Okay. Now all the processes, let me take P1, P2, P3, P1, P2, P3, right? Okay, let's have only three examples, P1, P2, P3. So processor enters the CPU. Now all these are put into ready queue. Okay, ready queue means these P1, P2, P3 are ready to execute in the CPU. Okay, this is the meaning of ready queue. Now coming to the wait queue, the processors, let me take the same P1, P2 and P3. Okay, P3. Okay, so these processes that are waiting for a certain event to occur, what that certain events such as completion of IO are placed in waiting queue, means these processes, right, assume that in ready queue also P1, P2, P3, they are waiting for the CPU. Once they get the CPU, they completes their execution, and after completion of their execution, if any of the process wants a IO operation to be performed, then again those are put into waiting queue, right? Again they are put into waiting queue because they want the IO devices to perform their operations. So again this is the waiting queue. This is the waiting queue. Okay. So these are waiting to go back to the ready queue. Okay. So they came from the CPU from the ready state to waiting state because they wants to perform some IO operation. So any of the process, right, so that are waiting for certain events to occur, so those are called as waiting queue, wait queue. So already we have discussed in the process state, the process is waiting for some event to occur, IO operation, will put it into the waiting state. Okay. Okay, after knowing this, let me tell you this giving diagram which represents a process scheduling. Okay. Now here what happens, there is a ready queue. As I said that P1, P2, P3, right? P1, P2, P3. So three processes are in ready queue. So they are waiting for what? They are waiting for the CPU. They are ready to execute in the CPU. Once all these three processes gets into the CPU, right? So any process which wants to perform some IO operation, then they will put it into, okay, where is, this is the wait queue. Okay, they will put it into the wait queue. So IO request. So any process is requesting. So let me take P1 is requesting, then P1 will be put it into here, IO wait queue. Assume that another P2 process, its time slice is expired, means it needs more time than what the CPU is allocated. Assume that CPU is allocated 5 millisecond, but P2 did not complete its execution. It requires 10 milliseconds. So it will put into the slice expired queue. Again it will go back to the ready queue. One more time the CPU will assign the time to P2 and it will complete its execution. Okay. So if any process is creating its child process, let me take P3. Okay. Now again that P3 will come to create child process. It will create a child, right? So child termination wait queue. So it will come here, right? Then it will again go back to the ready queue. Okay. Similarly, wait for an interrupt. Any interrupt is happened and temporarily any process is resumed for a while, then it will put it into wait for an interrupt queue and it will come to interrupt wait queue and interrupt wait queue to ready queue. So once all these process means the processes completes its execution in the CPU, they will be terminated. So this arrow will show you the termination of the process. So this is how this scheduling queue works. Hope you understood this concept. So thank you for watching.